Alright, so I thought it might be helpful if I went through the solution to the test. And so let's do it. So problem number 1, suppose v is an eigenvector with eigenvalue lambda 1, likewise v2 is an eigenvector with eigenvalue lambda 2 for a matrix A if lambda 1 not equal to lambda 2. Prove that v1, v2 is a linearly independent set. Alright, so I suppose that AV1 is lambda 1 v1, AV2 is lambda 2 v2, with lambda 1 not equal to lambda 2, and also v1 comma v2 not equal to 0. These facts should appear somewhere in your solution as they are kind of critical to the proof. Now, I suppose that I have this linear combination equal to 0, right? So I'm gonna go with the direct proof. Then what I'm going to do is I'm going to multiply by a minus lambda 1 times identity. And that gives me a minus lambda 1i times v1 plus c2 a minus lambda 1i times v2. So let's see here. Let's talk about what some of you did. Some of you multiplied the matrix on the right. This is not good. We multiply matrix on the left of column vectors. I think you guys know that. Let's see here. So you multiply through, and what happens? A hits v1 and gives us lambda 1 v1, which I already explained up here. A hits lambda 2 v2, hits lambda 2 v2, as I told you up here. And so what happens? Well, these guys cancel out, right? And that just leaves us c2 difference of the lambdas times v2. Now, alright, so what's that tell us? That tells us that c2 times the product of the difference of the lambdas must be 0 since v2 is non-zero, right? But we knew that the lambdas were distinct, hence we get that c2 must be 0. But then returning to star our initial assumption, that gives us that c1 v1 is 0, but since v1 is not 0, that gives us that c1 is 0. So we got c1 equal to 0, c2 equal to 0, therefore, since we've shown that that's an implication of star, it follows that v1 comma v2 is linearly independent. Now, of course, you could also do this by contradiction. If you assume that one is a linear multiple of the other, you can work that out. I think we did both in class, and of course this was also on quiz 3, as you guys know. Alright, next up here. Suppose A is invertible. Lambda is an eigenvalue for A. 1 over lambda is an eigenvalue for A inverse. Prove that, alright? So, first of all, if A inverse exists, that means that the null space of A is 0. Therefore, lambda is not equal to 0. In other words, there is no 0 eigenvector. This is important because you need to divide by lambda. How can you divide by lambda unless you know it's non-zero? I don't think anybody stopped to check this important fact for the solution. I didn't take off too much for that if everything else was right, but technically that ought to be there. Alright, so it follows 1 over lambda exists. Great. Suppose AV is equal to lambda v for v not equal to 0, which is to say that v is an eigenvector with eigenvalue lambda. Since A inverse exists, we can multiply on the left. Some of you multiplied on the right in this problem. Not good. Not good at all. But whatever. Let's see here. Multiply on the left, because matrix times matrix makes sense. Vector times matrix does not make sense since we work with column vectors. Alright, anyway. A inverse A is, of course, AV is lambda v, right? And so, if you look at that, well, that's the identity. So what we get is v is equal to lambda A inverse v. Great. And since we know lambda is non-zero, we can divide by it, and that gives us A inverse v is equal to 1 over lambda times v for this non-zero v, which shows you that v is an eigenvector with eigenvalue 1 over lambda. And so, we proved it. 1 over lambda is an eigenvalue for A inverse. Now, some of you tried to do some things with like the determinant being the product of the eigenvalues, and that's a nice idea, but the trouble is you can't isolate the factors in the determinant because the way things factor, it's kind of complicated, and so as far as I know, this is the argument you got to give here. Anyway, others of you have assumed A is 2 by 2. This is more ridiculous because A is not given to be 2 by 2. You shouldn't make A 2 by 2 unless it's given to be 2 by 2. When you make A 2 by 2 matrix, when it's not given to be 2 by 2, it's not good. All right, anyway, let's go on. Okay, so next up here, And I'm trying to make some corrections here. In my original solution, I think I had a 3 here because I failed to remember that I had a root 6 to normalize this vector. So I fixed that here. So we got v1, v2, v3, beta. And I constructed these, and, you know, given that this test is about what? Eigenvectors and orthonormal stuff, you know, first thing I would do if I was a student would be check, hey, is this basis already orthonormal? What's going on here? What's the deal with this? And it's pretty easy to see from this. This has length 1, this has length 2, divided by 2, which is 1. This has length 1 again. These are all unit vectors. And if you start taking dot products with these, it's fairly easy to see that these are in fact perpendicular, because dot product of this and this is 1 minus 1 divided by root 6, which is 0, and this, anyway, this is an orthonormal basis, all right? So since it's an orthonormal basis, we can calculate the coordinate vector by taking dot products. 3, 2, 3, and so I do that, all right? And a few of you got that, which I was happy. Many of you have done other things. I don't know how to characterize what's been done, but some of it was very, what's the word? Abstract. Some of you just tried to calculate straight up from like the back, you know, I mean, yes, it's true that, let me find my marker. I mean, no, you know what, I'm not sure I want to do that. Oh, fine. I mean, it is true, of course, that, you know, x beta is equal to beta inverse times x, right? I mean, fine, fair enough. But you really don't want to do that if you can help it. And because beta is an orthonormal basis, that's actually equal to beta transpose times x, which, by the way, amounts to, you know, well, x dot v1 x dot v2, x dot v3, of course, which is what I already calculated. So anyway, I don't know. What can I say? The spectral theorem in reverse, this was an example we did in class. I showed you guys we can build a matrix with eigenvalues of our choosing, given an orthonormal basis of our choosing. I guess if I have any regret here, if I wanted to remove any sort of excuse you had in this problem to not get it, I should, maybe if I had said something like, maybe if I had made part, you know, the preamble to part A, is beta a special kind of basis? What properties does beta have? Perhaps I could have asked that question. I don't know. Something to get you guys to see that's an orthonormal basis. All right. If this was not an orthonormal basis, though, that would have been a more appropriate question for the previous test. So, yeah. Oh well. I guess fair enough, on the final exam, I wouldn't assume that beta is orthonormal. I mean, it might be, it might not be, right? Because on the final exam, it's comprehensive, so who knows if the basis is a special basis like orthonormal, or if it's just a plain old basis. I mean, plain old basis, fair enough. You got to go back to calculate the inverse matrix to find the coordinates. That's true. But this was a special basis. It was orthonormal. All right. Sorry, the papers are getting askew. So the spectral theorem in reverse, and I think about 5 of you got this. I don't know, something like that. I think only one person actually got to the point of writing this matrix out. Some of you wrote something like this or something close to it, and that was good. But you know, this is an example I share with you guys in class, and so there it is. Now, some of you wrote 6, 10, 0, the diagonal matrix 6, 10, 0, and it is true that that matrix has eigenvalues 6, 10, and 0, right? But what the problem with that is that it doesn't have v1, v2, and v3 as eigenvectors, as was requested in the problem statement. All right, next up, problem 4. All right, so I did problem 4 2 different ways to show you guys 2 different ways to think about it. I said find a basis for W perp and the point in W closest to 2, 3, 4, 13. So the fact that the null space is the span of that is not obvious, all right? Let's see here. I'll show you the calculation. So what I did is, of course, row reduce the the matrix for that set transposed, which makes these column vectors turn into row vectors, right? And then row reduction gets me over to here. I didn't bother to put it in our REF because it's already clear that these are the pivots, and okay, fine, I could permute the last two rows and get the row ref technically, but reduced to echelon form. But there it is anyway. So with that, I can see that x in the null space of this matrix is in fact x4 times 1 minus 1 minus 1, 1. All right. And so that's the basis for W perp is 1/2 of 1 minus 1 minus 1, 1. The 1/2 to make it a unit vector, because then I can calculate the projection onto W perp pretty easily. All right. Well, so we know that the sum of the projection onto W and the projection onto W perp is the whole is the identity operator by the theory of orthogonal complements, and so but this is easy to calculate because it's just that one vector, And so here's the projection onto W perp, just a dot product with the unit vector and the basis for W perp, and that picks off the part of the vector 2, 3, 4, 13, which is in the W perp direction, which happens to be 2 minus 2 minus 2, 2. But then, since I know that the sum of this vector and, well, I can subtract this vector from that to get the projection onto W, and that's what I do here. And that gives me 0, 5, 6, 11. Now, none of you tried to do it that way, and that's fine. I kind of thought you might not, and that's why when I made the test, I added some white space so that you'd have room to do it the way you're probably going to do it, which was this way. All right. So the other way to do it, of course, would be to find basis. Now, I guess technically speaking, even if you find a basis for W, you still need to find a basis for W perp because of my instructions, right? And so, well, I haven't really addressed that from the perspective of this solution, honestly. I suppose that if you ignore the first line and you just run Gram-Schmidt algorithm on the basis for W, which is given, first of all, the first two things are already orthogonal. They're just not normalized. You divide by root 2, divide by root 2. A lot of you did that. I was happy to see that. A lot of you got that much. And then a lot of you ignored the fact that this was not perpendicular to these two guys. So you have to run the Gram-Schmidt on this to orthonormalize it. And some of you tried, and the arithmetic went sideways or something. And then, that's a relatively small problem if that's the only thing that went wrong. But anyway, so here's how to orthonormalize. The Gram-Schmidt algorithm says subtract off the U1 and U2 hat pieces like that. And when I do that, I get 1/2, 1, minus 1, 1, minus 1, 1. This happens to, amusingly, this is already a unit vector, which is kind of funny. That doesn't usually happen, but it did this case. So that's an orthonormal basis for W, so we can calculate the projection by just taking dot products onto the respective unit vector directions and multiplying by the respective unit vectors. That's the projection formula. It has to be, again, we need orthonormal basis to make that work, and there it is. And so there you go. Hey, look at that. We found that a rather different way just a second ago. So 0, 5, 6, 11. Okay, so suppose that you were in this world, you'd calculated this basis, U1 hat, U2 hat, U3 hat. It's an orthonormal basis for W, but you had not done the calculation on the previous page to find the basis for W perp. Well, how would you find a vector which was, a basis for W perp? Well, you'd want to find something that when you put this, 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 and that fourth vector together, you get something that is what, a basis, or well, more specifically, you need something that's, you need the fourth vector which is perpendicular to these first three. So, I suppose you could guess something. You could try you could have tried a unit vector, and then you could have subtracted off the pieces of the unit vector which were in the direction of this, this, and this. I don't know. I mean, if you do it this way and then attack the problem of finding the basis for W perp, there's kind of a non-trivial calculation to do there. So that's why I asked you to find the basis for W perp to start with, was in the hope that you might possibly might have thought of the way I did it the first way, because it's a little bit easier. But anyway, I was happy if you did it this way and got it still, you know? All right, let me go on. Number 5. Number 5, I would say, so when I read solutions to number 5, I'm reminded of the game of telephone, where, you know, people sit in a circle of chairs, and one person tells the other the rumor, and they each whisper it in the ear of the next person, you know, and go around. And so to me, that's kind of like what I felt like when I was reading proofs here. I felt like I could tell at some point there had been studying of the actual proof, and then somehow it got lost in translation. And so there's, you know, it's I guess it's the danger of with oral traditions, but anyway, so I don't know what to say. We proved this in class. You know, this is a pretty standard problem. But here goes. So suppose you have a set of vectors. They're non-zero. They're orthonormal. This is an inner product space. Some of you are saying dot product. I mean, it's possible this is a dot product, but it's not given. Inner product is more general than dot product. Prove S is linearly independent. So, okay, so as usual, we'll suppose that you have a linear combination equal to 0. Then take the inner product of that with Vj, where j is arbitrary. Of course, the inner product of 0 with Vj is 0. And this guy, on the other hand, simplifies this plus this. Now, a lot of you had the right idea, but you forgot that you need to focus your attention on the jth one in this sum, right? So you got like, this is 0, this is 0, this is 0, and then magic happened, and they're all 0, right? Well, you know, I can kind of tell that you're not thinking when you do that. You know, I'm supposed to try to grade these things, and what can I say? This is the issue. This right here is the one thing that's non-zero, and that is non-zero because that's the length squared of the vector, which is non-zero because we're given that Vj is non-zero. So that gives us that Cj is 0, since this is non-zero, and we have the product of this and that 0. But since j was arbitrary, that proves that C1, C2, all the way up to Cn is 0, which is to say that S is linearly independent. So there you go. Of course, I would point out that we did do this proof in class, and it's a pretty standard question. Anyway, now this, I think, is where the most people had the most right. This problem, number 6, was the hero of the test, let's say. So most of you have this x plus y. Now, those of you who got it wrong did something. Again, I feel like the game of telephone is you know, relevant because I could see that you'd studied this, right? But your starting point and the steps in between were, well, just not right. All right, anyway. So, you know, ideally, when you do this, you say some things like, my solution even is not quite complete. I really should say something like by bilinearity, you know, and here using the symmetry, because I says a real inner product. So, like, some of you had a conjugate here. That was not necessary because it's a real inner product space. So that means that, like, the inner product is symmetric, so that gives us 2 times the inner product of xy. But of course, x and y inner product is 0 since they're orthogonal. All right. Anyway, moving along. Excuse me. Now this one here, if you look at the solution I have posted, I missed something in my first go through this, and I was in a little bit of a hurry, and I completely forgot about that one. So it's easy enough to miss a case, and you know, a lot of you have given me redundant Jordan. So when I ask what are possible Jordan forms for a problem, what I really should say is, you know, possible Jordan forms up to reordering of the blocks. Like, I don't really care about, I mean, I care, but it you know, the thing I'm really trying to test on here, I don't really much care if you take this block and that block and permute them. Like, it's the same Jordan form. If I write this, then this, or if I wrote this, then that second, you know. Like, if I juxtapose the blocks here, flip the blocks, to me that's the same Jordan form, because Jordan form is up to the reordering of the blocks. Okay, fine, that's the departure from uniqueness. So some of you, and so, I mean, fine, you just read the literal problem. I get it. I'm not really fussing about that. What I'm fussing about is missing if you miss one of these cases. And you know, this is a harder problem in some sense, and so I'm happy if you got at least some of this. And I'm understanding if not everybody got this, that's okay. I mean, not everybody's going to get this problem in a given year. But the larger point here is this is an eigenvector, that's an eigenvector, so we have two eigenvectors. Each Jordan block has at least one, each Jordan block has one eigenvector, I should say. So this already tells me that there are at least two Jordan blocks, all right? This, on the other hand, is a generalized, V2 is a generalized eigenvector of order 2 for eigenvalue 3. That means that there's at least one Jordan block which is 2 by 2. All right? So this V2, it can either go to make like this 2 by 2 block, or this 2 by 2 block, or the start of this 3 by 3 block. But the point is, we can't have all 1 by 1 Jordan blocks. That's not allowed because this right here basically says that A is not diagonalizable. All right? Now some of you gave me 3, 3, 3, 3, like just the diagonal 3, 3, 3, 3 is a possibility. It's not possible because of this. All right? Others of you gave me the 3, 3, 3 with 1s on the superdiagonal. In other words, J sub 4 of 3, right? The 4 by 4 Jordan 4 block with eigenvalue 3. That's also not possible because we have two eigenvalues. So we're stuck in the middle. We have to have at least two eigenvectors, and we can't have no generalized eigenvector. We have to have one. So we can either have a generalized eigenvector order 2 and a generalized eigenvector order 3 and just have the two eigenvectors, or we can have two chains. So this is one, you know, something like V2 from this one, something like another kind of V2 over here. So two length 2 chains with eigenvalue 3. Or the other possibility is 1 2 chain and then, you know, having an eigenspace with dimension 3, as I said. So, you know, this is, to me, this is an easier version of one of the homework questions I asked you. I didn't even ask you about like minimal polynomials here, so it was just kind of a part of that homework question that Carson asked about one day. Okay, now problem 8. I am happy to say that I think everybody got this one. As far as I remember, everybody got that. So I was happy to see that, because that doesn't always happen. Some of you guys, sometimes in a given semester, people forget to study that. It's easy enough to do. So, and a lot of you got that the eigenvalues were 1 and 3. If you didn't get eigenvalues 1 and 3 and then you still did stuff after that, it's just all nonsense. It's all, I mean, you know in your heart that it's, once you had the wrong eigenvalues here and you go down here and work out the equations, you got 0 for the only vector solution. And so that's why I wrote it in for you. Anyway, eigenvalue 1, eigenvalue 3, it gives us this, you know, these eigenvectors, I divide by root 2 to normalize them. Then the formula, now, you didn't actually have to work all this out. I would give complete credit if you just went straight from here to there. Some of you have written that V is equal to this. That's just not true. Q of V is equal to this. All right, not V. V is not equal to this. V is equal to that. Q of V is equal to this. And the reason for that is because of these calculations, which, you know, again, I would have given you credit if you didn't show this. I'm just putting this in here to explain again why that's true. Whatever. And then the picture. Now some of you had an ellipse, but your ellipse was not tilted. Some of you had an ellipse which was not tilted in the right way. There's some various errors in the picture here. It didn't have to be as neat as the one I've drawn here, but it is something like this. The labels are important. If you were going to draw the ellipse untilted, then you should make y bar and x bar instead of yx. I mean, if you were to draw it untilted, your picture should look something like this, right? But anyway. So some of you had tried to do something three-dimensional in that last one. That would come from looking at like z equals to q of xy. That would be something different. I did talk about that briefly, but that wasn't that question. Sorry about that if I confused you. So this one here is actually a combination of the last problem. It's got that 2 by 2 block. We already know that has eigenvalues 1 and 3 from problem 8. And this guy, well, that's a real Jordan block with complex eigenvalue 1 minus 2i. So from the theory we've talked about this semester, I can see eigenvalue 1, eigenvalue 3, and 1 plus or minus 2i from that 4 by 4 block. So if you did do the calculation, you should have also found this. And if you did do the calculation, you should have gotten immediately the product of two 2 by 2 determinants, because the determinant of the block is the product of the determinant of the blocks. So your calculation, some of you are not knowing that, and you're actually expanding a 4 by 4 determinant here. That is unfortunate, because it is not that complicated. There's an easier way to do that calculation. So let me, here, I'll write that out just to make sure you know what I'm talking about. Let me not just talk. Let me write that out just in case. So suppose you don't know this theory I just told you about, right? So the determinant of a minus lambda I would be the determinant of 1 minus lambda minus 2, 2, 1 minus lambda blocks. 0 up here, 0 down here, 2 minus lambda, 1, 1, 2 minus lambda, all right? And there's a property of determinants that says that's the determinant of the upper block and the lower block. And if you don't know about that yet, well, now's a great time to learn, because if I do ask something on the final which involves you knowing this identity, not knowing it makes life much more difficult. But knowing it, it's just lambda minus 1 squared plus 4, and this is lambda minus 2 squared minus 1, which of course is lambda minus 1 squared plus 4. That's irreducible. And this one factors into lambda minus 3 times lambda minus 1. So of course this gives us the 1 plus or minus 2i, and this gives us the lambda equals to 3 or lambda equals to 1 solutions, which is what I just claimed before on the basis of the attachment of this problem to problem 8, or of course the real Jordan block with eigenvalue 1 minus 2i. So anyway, that's that. Oh, what have I done? There we go. All right, so getting back to the problem, the eigenvalue is 1, 3, 1 plus or minus 2i. Now, so already we can see it's not real diagonalizable because it has complex eigenvalues, right? So if all the eigenvalues aren't in the field, then it's not diagonalizable over that field. So it's not real diagonalizable. However, it is complex diagonalizable because 1, 3, 1 plus 2i, and 1 minus 2i are distinct eigenvalues. And we know distinct eigenvalues get distinct eigenvectors in the sense of linear independence, which means we have an eigenbasis for A over as a complex 4 by 4 matrix, or equivalently, the complexification of A has a complex eigenbasis. Anyway, it is complex diagonalizable, and this is what it would be similar to 1 plus 2i, 1 minus 2i, 1 and 3. And again, and you could shuffle these around. Problem 10. I'm sorry, you guys. I was trying to do something interesting, and I grossly miscalculated where you guys were. I should have made this much easier. It's my apologies. I've made this problem too sneaky. It was not my intention to confound all of you, but I seem to have done that, and so sorry. I will, if this comes back up on the final, I will find a way to make it simpler. The easy way to make it simpler would just be to replace A with J, right? Or replace A with the one we did in class. Instead of this, we had a 1 here, and that was what led to the caution cinch. When you put a minus 1 here, it ends up leading to cosine and sine. But anyway, with this J squared is minus I, in contrast to the square being I in class in the review day. But anyway, since I commutes with minus 2j, the matrix exponential allows us to calculate as such. So I get e to the ti times e to the minus 2tj, and e to the ti simplifies to e to the t times I by one of your homework problems. And this expands like so, but then the j's, of course, and the even j's or the odd j's simplify like so. So the even ones give us the plus minus. The odd ones give us the minus. Hey, seriously? Come on, again? Plus, I think plus. It should go plus minus, right? Anyway, and so what I got there, if I could, well, maybe I should put a minus. It'd be better to put the minus inside the cube. Because I wanted to look at his sine of minus 2 times j, because this is the sine series evaluated at minus 2t. This is the cosine series evaluated at 2t, so I got cosine 2ti minus, I could pull the minus out because sine is odd, right? I could do minus sine 2t times j. All of this times e to the t. There you go. Yep. So, sorry about that problem. Yeah. Sorry. This one, I have no apologies for. But pretty much nobody got this one. Sorry about that. But, well, some people at least did something reasonable. So I tell you this is orthonormal. I think you guys just ran out of time, which is understandable. But so this is orthonormal, that's orthonormal, and I give you a linear transformation that maps one orthonormal basis to another. And then I say prove or disprove it's orthogonal, right? And I chose prove. And so to prove it's orthogonal, I need to prove that the inner product of tx with t of y is just x and y again, right? And so if that's x and y, I can expand it in the beta basis. I can use the linearity of t, and I didn't say, I mean, if you'd made it real here, I would have been sympathetic to that. I was trying to be thinking it's possibly complex. I pulled out the conjugate from the second component, you know. And then these map to the w's, great. But w's are orthonormal. But the cool thing about it being orthonormal is means that this is equal to that, but this is also equal to that. And then you reverse the steps. Reverse the steps, because then we can pull the sums back in and convert this back to x and that back to y, and voila, there you go. There you go. This is equal to that, which proves that t is in fact orthonormal. And so, in fact, I would point out that if we have an orthogonal transformation, rather, then if beta is orthonormal, that implies that t of beta is orthonormal, since it preserves the inner product, right? So orthogonal transformations preserve orthonormality of bases. If you just have a plain invertible transformation, that will just take a basis to a basis, right? It's kind of interesting to think about what kind of transformations preserve what sort of basis. And that was the intention of this problem, but oh well. I think most of you will do better on the final, and I would expect the final will likely replace this test grade for most of you. And I'm sorry if it didn't go better, but do not despair, do not give up, just try your best on the final, and hopefully there will be more time to think, and hopefully you can think. So, see you Monday, I suppose. Thanks, guys.